Good afternoon, everyone. My name is Gal Oshry. I'm a product manager at AWS, working on SageMaker. I'm here with Emily Weber and Thomas Collar to talk to you about training and tuning state-of-the-art machine learning models on Amazon SageMaker. Before we start, how many of you are already training machine learning models today? Awesome. How many of you are training models with more than 10 GPUs or accelerators? All right. Anyone with more than 100? All right. 1,000? No. All right. Cool. Well, today we'll learn a bit about that. So we'll talk about the challenges for training large-scale machine learning models. And then we'll talk about how SageMaker can help you train those models. Emily will then talk to you about fine-tuning and pre-training large language models and show you a demo training Llama 7B on SageMaker. And then we'll hear from Tom about Toyota Research Institute and their machine learning use cases. So machine learning has already proven itself useful across a wide range of applications, from recommendations to credit risk prediction and autonomous driving to document analysis. But recently, there's been an explosion in interest in deep learning models for computer vision and natural language processing. Just a few years ago, this is the type of image you would get if you tried to generate a very clean living room with a machine learning model. You can tell that it's fake. It's not really coherent. You can't tell that it's a living room. And just a few years later, we can now generate images like this, where you'd have to look really closely to tell that it's not a real image. And I showed something similar a year ago at reInvent. And at that time, this was kind of shocking, right? Seeing this type of image get generated from a model. But a year later, and I think many people in the audience have already seen these types of images get generated and the quality that you can get with machine learning models. So how did this happen? Well, first, there were notable algorithmic improvements over the last few years, specifically the transformer architecture, which is used in many of the large-scale models that you hear about today. However, there's also an increase in the data sets, the model sizes, and the amount of compute that is used to train these models. And a lot of the research shows that we can continue increasing these dimensions to get better and better results. So to be competitive, you really have to think about how do you leverage these advancements to provide the best experiences for your customers with machine learning. OK, so training large-scale models is awesome. Let's just train the biggest one immediately and be done with it, right? But it's a bit more complicated than that. There are some challenges. The first is that you want to use the latest hardware. Every few years, there are innovations in hardware that lead to 2 to 9x improvements in training efficiency. But it's not enough to get access to the latest hardware. You have to think about how well it works. Is it fault-resistant enough to be able to let you to continue your training with minimal interruptions to the machine learning team? You have to think about orchestration and how to most effectively use the resources you have available, especially if you have a large team of data scientists who want to train many models in parallel. We talked about how you want to have larger data sets. And being able to store, load, and process these large data sets can require a lot of work. And there are a lot of pitfalls in doing that. You want to think about scaling up, both the infrastructure to get more compute for training the model, as well as the algorithms that you use. The models that we train today for these use cases do not fit on a single accelerator. So you have to think about the algorithms that you need to use to scale up. And finally, we have to think about cost. Training these models can cost hundreds of thousands or millions of dollars. So you need to think about efficiency when you're training those models, especially at the beginning when you're doing sporadic experimentation, you're trying out different ideas, and you don't use the hardware all the time, right? So you want to think about how you use that efficiently. And it's not just the financial cost, but the team's time, right? A lot of customers tell us that making sure that their ML engineers are not spending time dealing with infrastructure is one of their top priorities. But not all hope is lost. Amazon SageMaker can help with many of these challenges. I'll give a high-level overview of how SageMaker works, but you'll see it in a lot more detail during Emily's demo. We start by calling the Create Training Job API. This API captures information about your data set, your compute resource configuration, as well as the training algorithm that you want to use. SageMaker will then set up the cluster for training the model. with the right VPC and networking configurations by default to save you a lot of time, but you can configure all of it yourself as well and add the flexibility that you need. As part of spinning up the cluster, SageMaker will also run health checks on the hardware to make sure that everything is working effectively before the job even begins and before the billing starts. So this saves you time and money to make sure that the training can continue efficiently. SageMaker will then load data from S3, EFS, or FSX for Lustre, and you have options to either copy or stream the data. Depending on your dataset size, one of those might be more applicable. But again, and you'll hear this theme again and again, while SageMaker provides great options for getting started and moving quickly, you also have the flexibility to do what you want and load data from other sources. You can then download the training image from ECR, and you have options of built-in algorithms in SageMaker. You can use one of the SageMaker deep learning containers to quickly use PyTorch, TensorFlow, or Hugging Face, or you can bring your own training image with your own algorithms completely. SageMaker also offers distributed training libraries that can help accelerate both data and model parallel training, and you'll hear more about that later. SageMaker then starts the training and streams the logs to CloudWatch throughout training. It stores the metadata and hyperparameters, so you can view it later. And you have, again, options for using TensorBoard and other tools to visualize your experiments. It will synchronize your checkpoints throughout training to your storage, which is critical if you want to be fault resistant in case something fails during training. You don't want to lose your progress until that point. At the end of the training, SageMaker will save the model and other output data so you can revisit it later. At the end of the training, SageMaker spins down all the compute so that if the job fails at 3 a.m., no one has to wake up to turn anything off and make sure that you're not paying for all that hardware, all those instances running without being used to train a model. And with the same paradigm, we can actually scale up our training to many more instances really easily to get those large-scale models. One really awesome feature that we launched this year is a cluster repair feature. So if during the training, one of the instances fails, we look at what happened to that instance and decide whether we need to reboot it or replace it with a different instance, and then restart the training within a few minutes. So there are all these resiliency capabilities to ensure the training continues as quickly as possible and without manual intervention. In case any of that sounds intimidating, the good news, it's actually really easy to get started. The most important code for converting model training to a SageMaker training job is the estimator API. You'll see more in the demo later, but at a high level, the API takes a Python file or an entry point, in this case, cifar10.py, which is very similar to how I would do the model training on my laptop. I also provide the instance type I want to use, how many of them, and hyperparameters, which I can easily change later to try additional training jobs. I also add metric definitions so that I can view those metrics in CloudWatch during the training. Finally, I provide a path to my data and call estimator.fit. Now, the even better news is that we recently made it even easier to get started. Now, you can take your existing Python code and add the remote Python decorator to it to immediately serialize the runtime, the packages, functions, and everything else so that it runs as a SageMaker training job without even having to learn about the estimator API. Once the training job begins, you can easily view the metadata and reproduce it later or clone that training job. And tracking experiments is extremely important. You want to learn from what you've done before. And we often see people who keep the training results in a spreadsheet or even in a document and pass it around the team. But that makes it more difficult to collaborate and learn from past experiments. So by automatically keeping all of this in one place, it becomes much easier to learn from your mistakes and build better models. Now let's move on from tracking the training to improving the performance, specifically the training speed, which impacts how much time you end up requiring to use the instances to train the model and the overall project completion time, as well as the cost. Now, the SageMaker Profiler is an ML observability tool that enables you to understand hardware utilization and root cause performance issues to maximize the efficiency of your model training. On the dashboard shown here, we can see some overall metrics around the GPU usage, and you want that to be as high as possible, as well as the GPU usage throughout the training job across each individual node within your cluster. So you can see that even if your utilization overall might be high, within some intervals there might be low utilization that you want to check out a bit more. Lower down on the dashboard, there are other metrics. For example, the total time spent on each GPU kernel. So that gives you additional hints about what you want to optimize next to further improve your training. There's another page in the profiler showing a more detailed timeline view that allows you to get data from your host and devices at all the different levels. So you can dig deeper to understand what is happening at each point. Now, I'm excited to announce a preview of a new capability in SageMaker, smart sifting of data. Smart sifting is an online data refinement technique that can reduce your deep learning training time and cost by up to 35%. Now, when you train your models, and we talked about wanting to use larger data sets, it also matters about the quality of the data sets. And some samples in your data might be less informative to your model training, or you might have seen those samples already. There might be duplicate data or similar data. And it's often difficult to pre-process that data and remove the data that you don't want in the training anymore. So smart sifting helps because it analyzes your data during the training job and filters out the low-loss samples, which are less informative to the model. By training on a subset of your data, you can reduce the time and cost of the training by up to 35%. And because it only filters out the low-loss samples, it has minimal or no impact to the final training accuracy. And it's easy to get started because it does not require you to make changes to your data or training pipeline. Here's a simple example that uses smart sifting. We use the SageMaker deep learning container. We load the sifting data loader, and then we wrap whatever existing data loader we use with the sifting data loader and provide a bit more configuration to start using it. I don't need to change the rest of my model or data pipeline. And we already have customers who are seeing great results with this capability. For example, LG AI Research use it to get meaningful increase in training performance without any changes to the model accuracy. At re:Invent, we also announced Amazon SageMaker HyperPod. This enables customers who are training large-scale models to get all the managed benefits of SageMaker that we've been discussing today with a UX that they might be more familiar with, of being able to access the instances directly, using Slurm, and so on. It has similar resilient capabilities to what we discussed for training in terms of replacing faulty instances and enabling the training to begin a bit more quickly, saving up to 20% in time. It also benefits from the optimized distributed training libraries that also improve performance for both model and data parallel training. And I mentioned it provides more granular control over the cluster and what you're doing, being able to access the instances directly, install additional software, and make any changes that you want to the cluster to be able to fine-tune your training a bit more. Now, we've talked about training really large-scale models, but sometimes you don't need to do that. Sometimes you just want to fine-tune an existing model. And that's beneficial if you have an existing model, a foundation model, and you want to bring in your own data to fine-tune that model to a particular use case. So by bringing in your own data, you're making the model better than if you were just using an off-the-shelf foundation model. But it saves you a lot of time and money because you don't have to train that whole model from scratch. Now, the challenge is that some models are not open sourced, right? You can't download the model weights and fine-tune them yourselves in an existing SageMaker training job. But this has changed with enhancements we've made to SageMaker algorithms and model packages. You can now easily and securely customize third-party models by fine-tuning them on your private data. This provides end-to-end security. The model provider can provide their model without revealing their model weights. And you as a customer can fine-tune on that model by bringing in your own data without exposing that data to the model provider. And the final model weights after your fine-tuning are also only available to you. Now, this can be done with a variety of models and algorithms, for example, coherent models. And all this is easy to use and done through the Python SageMaker SDK that we were discussing earlier, and integrates with other SageMaker capabilities, like SageMaker experiments and pipelines. And of course, with SageMaker Inference, you can deploy the models at the end to use them for inference in production scenarios in a secure way. I'll now hand it over to Emily to talk about fine-tuning and pre-training LLMs on SageMaker.
All right, thanks, Gal. Great, so I hope you're as excited as I am about a lot of these new launches and new features. I should introduce myself. My name's Emily Weber. I lead our Generative AI Foundations technical field community here at AWS. And in particular, some of those launches, many of them came directly from conversations with you. Actually, we were listening with customers and chatting with you to understand key capabilities that you wanted to see in our training stack, and this led to a number of the features that you've just learned about. In any case, there are many ways to customize a large language model. Here I'm presenting them on two axes, right? So at the bottom, you have roughly complexity and then cost. Obviously, you want to be closer to the left. You want your LLM customization techniques to be roughly easy, because then, of course, that's faster for you to get started, and then that's less expensive. However, there is a progression of these techniques. Most customers will start with prompt engineering, which is a nice way to easily improve and then customize your large language model. However, it's not as accurate as some of these extra techniques that you can use. Most customers will move from prompt engineering into what we call a retrieval augmented generation stack, where you have some set of data, you're converting that data into embeddings, or that dense representation, and then retrieving those documents to interact with your consumers. This then can transform, if you will, into a fine-tuning stack. Actually, there's a bit of an overlap there, but in any case, you can take, as Gal mentioned, custom data, fine-tune your model to add that extra knowledge. All of these techniques, however, pale in comparison to the holy grail, which is pre-training, which is creating a net new foundation model. And so all of these techniques are available on SageMaker and well supported by the stack. So we're going to learn how to move from fine-tuning into pre-training during our session here today. Now, fine-tuning small models is really impactful. Here are a couple of reasons why you would consider fine-tuning a small model. The first is, of course, it's less expensive. You're going to use a smaller data set, possibly a smaller model, and then still improve accuracy because you're fine-tuning this model, but you're keeping your costs down. When you're working with a smaller model, such as something in the 7 billion parameters, this is inherently faster because the model itself is just physically smaller than some of those larger ones. And so the training time is faster, the inferencing time is faster, which means you can train more models and you can do more inferencing, again, with that smaller object. Because the object is smaller, it's easier for you to manage. And so, again, the storage requirements are smaller, so it's easier for you to copy the model. It's easier for you to put the model into your applications and your packages and your CI/CD pipelines and your repositories. Many customers inherently prefer the ownership that comes with creating new models, particularly through fine-tuning and then again pre-training. This allows you to increase the IP of your firm, and then of course you have more deployment options when you're fine-tuning, again, that small model. The more deployment options include serverless. Actually, I have customers who create and then fine-tune these small 7 billion parameter models compile them and then host them on Lambda and run them on serverless inferencing. And so absolutely, when you're working with these tiny models that are knowledgeable in small domains, you have a lot of flexibility. Pre-training is really best for extremely large data sets. So when you have hundreds of GBs or multiple terabytes of custom language data that just really is not online, the language data that you have, if it's not in Wikipedia, if it's not on Reddit, if it's the core language that you're using, if when you take a sentence and try and put that sentence into Wikipedia, for example, if Wikipedia doesn't understand what you're trying to say, you may want to consider seriously customizing a language model and then possibly creating a new one from scratch. Now, why is this the case? Why is pre-training so powerful? Part of this is because the pre-training loss function is more generalizable. So when you're creating that new foundation model from scratch, the learning is slightly different. It's more general, and it's deeper in the neural network, actually. Also, when you're creating a new foundation model, you can do this without supervised data. So you don't need to go label millions of records in pre-training. You can just capture and tokenize a terabyte of your own language data and then throw that into the network. There's no need to add additional supervision on top of that, which makes it very attractive. Also, I love to see the efficiency gains of pre-training, actually. We all have small teams. We all have few resources for data science and modeling. And so when we take our small teams and focus them on one project and create this one massive, powerful foundation model, and then use the foundation model in many, many applications, it actually, I find, is more efficient than optimizing and then maintaining our tiny MLOps workloads, which is what many of us were doing prior to transformers. So what does it take to pre-train a new foundation model? It sounds scary. It sounds like only the best can do this. But in fact, in large part due to a very sophisticated and very mature training infrastructure that you're here to learn about, it's actually pretty accessible. So how are we going to do this? So here are 3 example models that were pre-trained and created from scratch on Amazon SageMaker, especially on our training infrastructure. Stable Diffusion, clocking in at 5 billion images and 240 terabytes of image data. And so, of course, that's a lot. And so image models tend to take a lot of data, but the models themselves are a bit smaller. And so you can use smaller cluster sizes. The Falcon model, of course, from Technology Innovation Institute, is a very large language model, the largest open source language model. 1 trillion tokens, just under 3 terabytes of language data, 40 billion parameters, and then 48 P4D instances. So sizable cluster, and that is 2 months to train this model. And then we have another financial large language model trained on SageMaker with just under 2 terabytes of language data. And so all of these requirements are surprisingly accessible, actually. I think there are quite a few companies with that volume of language data, and then the capabilities that we provide on SageMaker make the training experience, again, very accessible to a wide variety of companies. So how do we do this? If we know we meet the requirements, how are we going to go about creating and pre-training these foundation models on AWS? So the first step is just gathering and accessing that data. And again, we want at least, I'd say, 1 terabyte of your own language data. So this is documents, digitized PDFs, conversations, language streams, like rich, robust language data. So you want to gather about 1 terabyte of this language data. Many firms will then pair that with open source data, actually, so that your model understands both the nuances of your company's acronyms and history and phrasing and domain expertise, but also knows what time the sun rises in Honolulu, because of course we want that mix of the general sort of open source knowledge, but also what's specific to your company. And so that's gathering and storing the information. After that, you'll pre-process your data. SageMaker also has a really nice capability for pre-processing data sets. Actually, one of our builders, Jenny, over here, helped me run many pre-processing and data transformation jobs on SageMaker. And so you can use our training job API, including that remote function that we just learned about, to run jobs in parallel, which are then tokenizing and pre-processing. So this core sort of training job construct is applicable both for creating new models from scratch and also for general data transformation and general processing. So you'll pre-process your data sets, and then you'll optimize those data sets using your preferred data storage. We see a lot of customers using FSx for Lustre. This is because you can store your data in one place and then easily attach this volume to training job runs. So as you're iterating through different model sizes and different infrastructure and experimental choices, you can use and store your data in the same place. After this, customers will then need to develop and iterate over their training scripts, and the elasticity that you get with the infrastructure on SageMaker is beautiful. You can use and run tiny instances, so the T3 medium and the T2 that Werner shared with us this morning. So the T3 medium is a great choice for notebook instances, very cost-effective, very small machine. And then you can scale that up with a click of a couple buttons to a small GPU, for example, the G4 or the G5 series, which your teams can then develop on and get the nuances working in their training loop, and then ultimately scale out in the same platform, in the same service, to hundreds and thousands of GPUs. And so that's that move from step 4 to step 5, where you're developing and testing on increasingly larger instances, and then ultimately scaling up and using the massive training infrastructure that SageMaker provides. And then, of course, you'll evaluate the model artifacts step by step, and the way that SageMaker holds on to the metadata, holds on to your scripts, holds on to your hyperparameters, stores all of your artifacts in S3, makes it so easy to just look up your previous work. So, if you're trying to capture an experiment that you ran 6 months ago, or even 3 years ago, as long as it was in AWS, then you can easily go look up the result of that job, capture some of the artifacts, and then run a new experiment. And so at a high level, that's how you can pre-train foundation models on AWS. And again, all of this is possible because of the distributed training libraries that we provide on Amazon SageMaker. So these are capabilities that we've been building for many years, including data parallel and model parallel distributed training libraries that give you efficiency and enhancement. So model parallel is a way to distribute a neural network over multiple accelerators and GPUs, providing optimized performance. And then our data parallel package will let you actually make copies of your model across a large cluster. And then we're delivering custom communication collectives, actually, that are optimized for the AWS network topology to save you up to 40% in the overall training time. And so this is after many years of innovation at this layer in the stack. And again, all of this is available through SageMaker. And customers agree with us. So as you heard from Swami's keynote yesterday, Arvind Srinivasa, CEO of Perplexity AI, is happily using SageMaker, and in particular, the data and model parallel training libraries, again, to get that optimized performance, in particular in the hyperpod mode. Another feature of SageMaker that I find really handy is warm pools. And so the training job API, again, is creating infrastructure when you train a model. So when you call model.fit or when you run that Python training script, we actually turn on our instances at the same time. And so that call to create the cluster and to execute the scripts are coupled. They happen together. And now, again, this is really useful for cost efficiency so that when the job fails because I forgot to point to the right luster volume, that instance isn't sitting up there charging me money, right? It turns off, so it's extremely compute efficient. However, as a dev, that can be challenging because I don't want to wait 8 minutes just to ship a new line of code. And so we launched last year our warm pools feature that lets you run new jobs using the same image in seconds. And so as a developer, it's extremely handy because you can make just 1, 2, 3 line edits in your training script and then just run the job in seconds. And so the warm pool feature is incredibly useful for developing with the SageMaker training API. Another core feature of SageMaker is the ability to use many different types of instances and have a lot of flexibility with the underlying infrastructure where you're trying to run your scripts. One of these, of course, is custom accelerators from AWS. And so the Trainium and Inferentia capabilities are both available on SageMaker. And you're seeing a lot of cost performance relative to comparable Amazon EC2 instances, up to 46% with Trainium 1 relative to Llama 2. And so you'll see even better performance with Trainium 2, which was just recently announced. And so in the demo today, actually, we're going to take a look at Trainium on SageMaker. So what is this demo? So we're going to be pre-training Llama 2. Of course, I got a little visual for you. So this is a cartoon llama with sunglasses on the Las Vegas Strip from Bedrock. And so we're going to pre-train a 7 billion parameter llama on SageMaker. Now, why are we going to do this? Why is this a useful exercise? Again, this is assuming I have at least a few hundred gigabytes of custom data, so really a sizable data set of my own language data. And then again, this is knowledge that's not generally available online. And so it's my own proprietary data set. So it's knowledge that wouldn't generally be found in say, a Wikipedia archive. This then drives in-domain accuracy. And so this small model will be very surprisingly accurate within that domain. Again, it won't know everything under the sun, but it will have a surprising amount of accuracy, again, in that data set and in that domain where you're training it. This, of course, then drives, as I mentioned earlier, ownership. It drives flexibility, and then that lets you, again, use serverless hosting and then ultimately cost reduction opportunities. And again, how are we going to do this? So I have some example notebooks. I'm going to walk through different instances. Again, that T3 medium, the train 1, optimized large-scale data stored on FSX for Lustre, and then some warm pools, and then again, that distributed training infrastructure. So let's check this out. All right, so here we are. I'm starting with the example notebook. So this is a publicly available GitHub repository that is using NeuronX, which is from the Amazon Annapurna ML team, and then Nemo Megatron, actually, which is from NVIDIA. So this is the NVIDIA distributed training framework, Nemo Megatron, and then we're going to be running that on Trainium accelerators. This also uses PyTorch and then the core torch run framework. All right, so first I am running this on a notebook instance, actually. So this is a SageMaker notebook instance. This is my sturdy M4 instance, and it's handy because, again, you can create a Docker image. So what I'm going to do here on my notebook instance is I'm pointing to a deep learning container. And so that's a fully managed deep learning container that we build at AWS and track and manage and update as the software frameworks change. We manage these deep learning containers, and then you can inherit our container in your Docker files and build on top of it. And so it's an easy way for you to make sure that your scripts will work in the AWS framework. So first I'm going to build that Docker image. Then I'm setting up FSX for Lustre for my optimized runs. I'm going to prepare my data sets using tokenization on the SageMaker training API, converting the Hugging Face weights to the Neo framework. Then I'm going to train Llama 2. So again, just a really simple Docker image. I'm just importing SageMaker, pointing to the deep learning container account, grabbing that image, and then this is a nice SH script that just builds a Docker image. So I've got my Docker image locally, and then this is pushed to what's called the Elastic Container Registry, so another AWS service that just hosts your Docker images. And so I'm pushing my Docker image, which is on my notebook instance locally, up to ECR in AWS. And so that's this process. Great. So I have my Docker image hosted. My second step is setting up FSX for Lustre. So this is using a CloudFormation template to deploy Lustre in my account. You can also do this through the console. Lustre sets up a two-way data repository with your S3 bucket. So as long as you have data sitting in your S3 bucket, you can enable a two-way data repository. So data will be copied through the service. The metadata will be copied through the service from the bucket to Lustre. And then as you write files to Lustre, those are then copied back to S3. So you can download it from S3. You can also mount the Lustre volume to your notebook instance as long as the networking is aligned, and then you can view the contents of that volume directly from your notebook instance. So I'll set this up here. Again, just downloading the CloudFormation template and then creating the stack in the relevant AZ. Once the stack has been created, then I'm going to prep my data set. And so my data set, again, is for LLM training, using that Docker image, using the SageMaker SDK, and creating a lot of hyperparameters. So hyperparameters for the data set pointer, the model pointer, some of my keys. I'm pointing to FSX for Lustre right here, and then setting up the file system input. And then as Gal mentioned, here is the PyTorch API. Now this is, again, a very complex example. If you are new to SageMaker, I would give you a really easy one. And so there are a lot of very accessible examples where you can train a model in like 2 lines of code, basically using Hugging Face, actually. But certainly the Python training scripts, you can bring your own packages and requirements.txt and be on your way very, very quickly. This is a complex example, but we have very simple ones that you can use to get started. So in any case, I'm importing a pointer to that container, actually. This is this Python object is pointing to the deep learning containers for PyTorch. And then this API is letting me define my own pre-processing function right here in the script. I'm pointing to a source directory, which can be a local file, can also be a Git repository. And then I'm defining my infrastructure right here. So this is one Trainium, actually, .32xl. And so I'm running this job here. And again, that's my pre-processing data set. I'm going to jump to Llama here, because we're a little short on time. And so once I've pre-processed the data and stored it on Lustre, which again then will replicate back in S3, after that, I'm going to train my model on that same Lustre volume. And Lustre is useful because it mounts in seconds. So when you're working with large-scale data sets, of course, it can be very computationally and time-intensive to copy them. And streaming can be a little bit challenging to set up. So Lustre is a nice way to store your data in a high-performance file system, which you can then mount in seconds using as many jobs as you want to, because the bandwidth scales actually as a function of mounts. So Lustre is a great high-performance data store. So in any case, we're going to set this up. And then same as last time, pointing to all of my hyperparameters, specifying that I'm using, again, 4 instances. Each of these instances has 32 accelerators, again, the Trainium accelerators. All of the hyperparameters for the 7 billion parameters that we're going to train here, my FSX for Lustre pointer, And then I'm going to launch my training job. So setting in the rest of my hyperparameters, again, pointing to that PyTorch API, loading in my scripts, and then I call model.fits. And as promised, all of the content for this job is loaded directly in the SageMaker control plane. So I see exactly when I started this, what the status was, where the artifacts are, when I ran this. I can view the outputs. I can step through the logs and see every piece of information that I need for my model, which then, of course, I can download it and build an entire app on top of this. And so with that, I'm going to hand over the stage to Tom, and he's going to share some information with you about Toyota.
Great, thank you, Emily. So today I'm going to really tell you about how we're using SageMaker to accelerate machine learning at TRI. And first, maybe I should tell you a little bit about what TRI actually is. I'll give you a couple of example projects that we have ongoing right now. The first is a project around autonomous drift driving with a Toyota Supra. And I'll just let the video play here. So that's one example. And of course, AI here helps lay the foundation for all of this work. The second is we work on a lot of challenge problems. And so there's a big robotics group that focuses on challenge problems that we start in the lab, but also go out to the real world environment and evaluate our systems in. And so this is an example of where we have a robotic system that we built in-house from the ground up, and we're able to retrieve and stock grocery store shelves. This has evolved more into the factory setting as well more recently. And we're 250 people across a few different locations. So there's a team in Los Altos and a team in Cambridge, Mass. And there's teams also in human-centered AI and also material science as well. And most recently, one of the things about generative AI that we found anyway, is in the context of robotics, is that it can now be applied to robotics to be able to do a wide variety of tasks that we never thought were possible. And this is a technique called diffusion policy that is now able to learn from a few examples from a human how to perform very complicated tasks. And so building on this, the machine learning team at TRI tries to build a foundation across language, vision, and action. Language in the sense that both common sense knowledge and also a wider variety of applications. So like language has applications across Toyota more generally in the context of enterprise applications, but also in terms of code generation as well. Vision feeds into language to give robots eyes, for example, and then action to perform a wide variety of tasks across a number of different platforms. But this talk is more about SageMaker. And so I want to tell you about how we're using SageMaker at TRI to really accelerate our progress. And the first is sort of general experimentation, where we use sort of 1 to 8 instances to scale up our training jobs. And the second is how we can take some of these ideas and really scale this up very, very quickly to not just a few GPUs, but to hundreds of GPUs at a time. And finally, we're also able to use SageMaker for even more broad applications, such as like just serving models, as these are hard to serve sort of locally on a device. So let me tell you a little bit about the experimentation that we do on SageMaker at TRI. First, here's, I guess, the high level is that we have a wide variety of applications that models that we're training on SageMaker. The first is large language models. Second is a mono-depth model, so taking RGB images and inferring depth, for example. A third is sort of stable diffusion, language to image generation, for better feature representations. And a fourth is 3D representations, such as language to 3D sort of structures as well. That's useful for robotics and a number of other applications. And across all of these, we found SageMaker to be very useful for a number of reasons. Some of the challenges that come up for us include a few things. First, we want to be able to reuse existing training infrastructure and clusters that we create. And so, warm pools that you heard about earlier are one way in which to do that, and we take advantage of that on a daily basis to pull back those resources and continue iterating on our training jobs. The second is for scaling. We need to be able to go from one to many instances very quickly, and also to change instance types very quickly as well. We also need high-performance systems. So, and SageMaker is very well optimized in the back end. And finally, we need a sort of flexibility. We need to run a number of different jobs across all of the sort of science group. And so, I'll echo this is the code you saw earlier. I'll echo how easy it is to sort of scale these things up. You can start with one instance, and you can iterate with your training job with that instance, for example. And if you need to scale, it's a very simple change to enable that. So this can, in this case, you can change the instance count to from 1 to 8, for example, and then start just scaling your runs very quickly. The second is as new hardware comes out, as Gal mentioned, we're able to quickly change the hardware types as well. And so in this case, we can change, say, from a P4 instance to a P5, which will give twice the throughput for our training jobs and reduce sort of the training times for us. And just to give some evidence of how this looks, how performant these systems are, if you look at sort of scaling across a number of instances, it's almost linear in terms of the scalability here. So SageMaker has been very performant for us in terms of scaling up our training jobs as well. As Emily mentioned earlier, using these data sets are huge too. And as we started using data sets of a few terabytes, and it's nice to be able to quickly start up with FSX for Lustre. However, as we've scaled our training jobs as well, and the amount of data that we need for these, from a few terabytes to half a petabyte or more, the flexibility in SageMaker to pull in other resources like web dataset has been really, really great, and has really accelerated sort of the training runs that we have as well. And so, just to reiterate, I mean, there's the group is running jobs from one instance, 8 instances, and these are a few of the applications. But going beyond this, we're also able to scale our training runs to much larger scale as well here. And so, just to highlight one of the ways in which we're doing that at TRI, we're building sort of state-of-the-art. The question is, how do you build can you build state-of-the-art LLMs with SageMaker? And we at TRI have been doing this. We've been reproducing some of the Llama 2 models initially to validate all of our systems. And for this, SageMaker, we need sort of scalability and performance across all of these instances. And what SageMaker has really provided for us is that scalability. So this is the newest hardware, the H100s, and sort of linear scaling as the sort of number of nodes increases. And this is, so this ends up being like 256 H100s, and if you run this out, a training job like this for pre-training a Llama 2 model, can take about a week when you start scaling out to 30 instances. And this is just to say, with more than 1 trillion tokens, we can reproduce sort of like the state-of-the-art models here. And we're scaling not only from the 7 billion parameter models up to 13, 34, 70 as well on SageMaker right now. One of the key features, or one of the nice features of SageMaker, so that you don't lose any time, has also been some of the repair work. I think Gal may have mentioned this earlier. So your job may actually, as you scale these jobs, it's often the case that hardware will fail. And when hardware fails, you have downtime. And if you have downtime, it costs you money. You're not training your models. One of the great parts of SageMaker is that it has this option for cluster repair. And so for us, this happened in about 10 minutes. Like one of the machines failed, and the cluster came right back up, and we were able to continue our training run very quickly. So that's pre-training. And the other thing is that is sort of more on the side of uptraining, where you have a large data set and you want to, but not quite the size you'd need for pre-training, and you want to look at a particular domain. So we at TRI because we're a Toyota-centric entity, Japanese was sort of like one of the areas that we were very interested in. And so, you can take some of the state-of-the-art models, which aren't actually trained for, they do have a little bit of, say, for example, Japanese training data, but they don't have that much. If you go out there and acquire all of, say, the open source data available, you get to 10 to 100 billion tokens here, which is enough to uptrain a model such as Japanese. And what we found is that, taking Llama 2 with 13 billion parameters and uptraining, you gain some performance. This is a win rate metric against some of the best closed source models. But the next step, where you actually instruction fine-tune the model, so this is how you get large language models to follow instructions, to be sort of chatty, is to fine-tune them using instruction fine-tuning with data of this type, where the instruction in the first part would be in the first part, and the second part would be the sort of response you would expect. And if you do that with the additional pre-training, with the additional instruction fine-tuning in Japanese, on some of the more performant models out there, you can get state-of-the-art performance in Japanese here. And so this is a much smaller model compared to, say, a Llama 70B, yet still more performant, for example. And so SageMaker has really enabled us to do a lot of this experimentation very rapidly at TRI. The final one I just want to mention, it's not covered as much in this topic, but there's also the ability to do other sort of workloads, such as serving models as well. And we've been leveraging SageMaker endpoints to actually serve both open source models, as well as the models that we have in-house, internally across TRI, and maybe eventually externally as well. So with that, I just wanted to say there's sort of three primary areas which we're focused on using SageMaker for. Small-scale experiments, such as 1 to 8 nodes, for example. Large-scale training, up to 30 to 64 or more instances, as well as serving as well. And so, SageMaker has been very critical and important for our training of this variety of models and experimentation generally. And I just wanted to close, I guess, with saying, it's been great working with SageMaker for training all of these models. In the next time, hopefully, when we come back to AWS reInvent, maybe we will have a foundation model that can be trained once and do many different robotics tasks in response to language and other things as well. So with that, I'll end, and maybe I'll give Gal a thing.
Thank you, Tom. Yeah, we just wanted to end by showing you a couple of links, QR codes to learn more about SageMaker and how to use it. And thank you all for your time. We'll all stand around here for a little bit longer if you have any questions. And I actually think some members of the Smart Sifting team are also here if you have questions about that and want to learn more.